Today we're going to be looking into the remainder of the course material and just sort of start things off. Okay, last time we had looked into systems of equations, and for what we have with systems of equations, again, we had like linear, nonlinear, but let's say that within the official classification of what we have for systems of equations, there will be three particular types, okay, to look at, okay, and the ones we've been looking at have fallen in the category of those that are consistent and independent. Okay, so for what we have for those systems, again, which we have to be consistent and independent. Those systems will have a finite number of solutions. Okay, that is a limited number of solutions. Another classification is going to be with what we have as an inconsistent system. And for this type of system, there will be no solution. And then we have with the third and remaining type classification, we're going to have those that will be consistent and dependent. And this type of equation system, okay, this is going to have an infinite number of solutions. And to illustrate, okay, what we have for the possible classifications, okay, say if we were to determine the type of system for the following. Or say if we were to determine the classification of each system. And we'll say that we have in the first case, right, say if we have a couple of linear equations in x and y. We'll say that we have x plus y is equal to 7. And we'll say that we have negative x minus y is equal to 10. All right. So here we have equations in x and y, and we're trying to find those values of x and y such that the sum will be 7, and where the difference of their negatives will come out to 10. Okay, so here we have additive inverses, and it turns out we have in both the variables x and y. Okay, so I can add the equations together. So we have x plus y is equal to 7, and we have negative x minus y equals 10. And if we combine, okay, what we have in x and y. So if you notice, you have x's will go out. Also going to have the y terms will go out. And guess what? The whole left-hand side of the equation is going to be 0. But for what we have to the right, we got 7 plus 10 is going to be 17. And guess what? To say that there are going to be any solutions for x and y that will fit into both of these equations amounts to trying to say that 0 is equal to 17. Okay, so we have a false statement for the resulting equality statement. So we have no solution in consequence. And for the type of system we have which has no solution, that is going to be inconsistent. Right, so again, inconsistent system has no solution. Now, I say that if we have another system, and we'll say here that we've got x plus y is equal to 7. So we'll have that introductory equation again. So we have x plus y is equal to 7, and we have x minus y is equal to 1. Okay, so you have a linear system of equations, and this time we have additive inverses only in the variable y. Okay, so you have x plus y is equal to 7. And x minus y is equal to 1. And if we apply the addition method, okay, we'll have only the y terms to cancel. Okay, so adding the equations. Okay, so we'll have x plus x is 2x. And we have that 2x is equal to 8. And we're going to have that x is equal to 4. So we have that x is equal to 4. And if we look at solving for y, again, I can plug in 4 for x into either equation. Now I'll just plug in for x in the first. Okay, so we got x plus y is equal to 7. And again, we have that x is equal to 4. So we have that 4 plus y is equal to 7, and from this we have that y is equal to 3. Okay, so x is at 4, y is at 3. 4 plus 3 is 7. Also 4 minus 3 is equal to 1. Okay, so we have for the solution, again, we have just itemizing what we have for x and y. We had that y is at 3 while x is at 4. And you can write this in ordered pair terms. And since we have just one solution, that is a limited number of solutions, the type of system we have is going to be consistent and independent. Okay, and now another scenario. Okay, say if we have where we don't have additive inverses in either x or y, but still being able to set up a system of linear equations. Let's say we have x plus 2y is equal to 7. And say for the other equation we have negative 2x minus 4y is equal to negative 14. Okay. And for what we have in this case, all right, we have two equations, okay, and we don't have additive inverses in x or y, but I can make an adjustment where we can form the presence of additive inverses. Okay, and you can either cancel out the x terms to solve for y or vice versa. And let's say that if we work with x, okay, so you have x and negative 2x. Now, if I were to cancel out the x terms, I can take the additive inverse of negative 2x with 2x. So to raise the x that I have from the first equation to 2x, I'm going to be looking at doubling all of the first equation. And upon doing so, we have in doubling the first equation, so this will become 2x plus 4y is equal to 14. And again, just leaving the second equation as it is, so negative 2x minus 4y is equal to negative 14. And so for what we have here, now the goal, okay, initially was to get the x terms out, okay, but it just so happens that by doubling the equation I end up with additive inverses for both x and y. And this time, okay, this is still going to work out. You'll have your x terms and the y terms to cancel, and guess what, the constants on the right with 14 and negative 14, they will also cancel. Now before, we had that 0 is equal to 17, and so we wound up with an inconsistent system in the first case. But with 0 equal to 0, okay, that's a true equality statement. And this is going to consist of an infinite number of solutions. And let me mention, okay, so you're going to have for x, okay, if you have a true equality statement, kind of goes back to the days from the early stages when we had like our types of equations like consistent, inconsistent, and identity. And this is like the system form of an identity, okay, where you're going to have an infinite number of solutions. And for what you're going to have in the case of x, the solution of this is going to be the set of all real numbers. Okay, and especially like in the case of Alex, okay, for all real numbers, you're going to put in terms of what we have for x. But for y, now while the range will also be the set of all real numbers, Alex is particular about how to express y, and that is to express it in terms of x. So for what we have in this case, right, so you have x plus 2y is equal to 7, and putting y in terms of x. Okay, so if I isolate the y term, okay, so you have taking x away, okay, so you have that 2y is equal to x plus 7, and if I divide by 2, we'll have that y is equal to negative x plus 7 all over 2, or negative 1/2 of x plus 7/2. And so for what we have in the case of the outcome, So you will have in the case of the solution. Okay, so you have for x at the set of all real numbers. And if they're my choosing, I would say that for y it had the set of all real numbers. But in case of Alex, it wants that y to be expressed in terms of x. We have that y is equal to negative x plus 7 all over 2, and you have that running throughout the whole real number system. And so for the type of system that we have, again, we have an infinite number of solutions, and this system is going to be consistent and dependent. Alright, so I just want to mention this, okay, for what we have with the classifications of systems of equations. Alright, and we have with numbers 14 and 15. Okay, 14 we have a linear system, 15 a non-linear. Again, we have with 14 okay, so 2x minus 3y is equal to 7. And the second equation, okay, so you have 4x plus 2y equals 26. And looking at what we have and working with number 14. Okay, all right, so we don't have additive inverses. But we can make an additive inverse set out of what we have in x or y. Alright, okay, so we got 2x minus 3y is equal to 7, and we have 4x plus 2y is equal to 26. Okay, what I can do here is I can cancel out the x terms. And let's say that if I cancel out 4x, what I would need is for the 2x to become negative 4x. So I can adjust the first equation, multiplying by negative 2. And for what I have here, okay, so about negative 2 over the first equation, so we have negative 4x. And negative 2 over negative 3y becomes a positive 6y. We have is equal to negative 14. And again, I have the second equation fixed. Again, 4x plus 2y is equal to 26. And adding the equations together. So we'll have the x terms to go out, and then we'll have 6y plus 2y, which will be 8y. Negative 14 plus 26 is going to be 12. And dividing by 8. Okay, so y with 12 eighths. You can say we have y is equal to 3 halves, or as a decimal, you can write as 1.5. Whether you write as a fraction or a decimal, in this case, either approach works. Okay, now looking at solving for x, again I can plug in 1.5 for y in either equation. I'll just choose the first one, but it works for the second equation as well. Okay, so just plug in 1.5 for y. So we have 2x minus 3. Okay. And we have, in this particular case, we have 3 times 1.5 is equal to 7. We have 2x minus 4.5 is equal to 7. Okay, so got some decimals in the mix. And for what we have in the case of 2x, okay, so we have that 2x is equal to 11.5, and we have with division by 2, we have another decimal value, and 11.5 divided by 2, we say have 5 3/4 or 5.75. Okay, so for what we have in this system, okay, there's going to be one solution combination for what we have in x and y. Okay, so I have x equal to 5.75 and y is equal to 1.5. And again, you can write this as an ordered pair solution. We'll probably have x at 5.75 and y at 1.5. Okay, now just for what we have in the case of the nonlinear system, so here for 16, okay, so you have the sum of squares at 25, and then we have a difference of squares where we have x squared minus y squared is equal to 7. I think I can squeeze this in. Okay, so we have with 15. Okay, so we're looking at x squared plus y squared. It's equal to 25. And again, for the difference, okay, so we'll have additive inverses already established with positive and negative y squared. And what I can do is go ahead and add the equations together. So I have x squared plus x squared becomes 2x squared. And we have 25 plus 7, okay, so that will be 32. We have a division by 2. So we have the x squared is equal to 16. And we have with the square root property of equality. And go from x squared to x. So we'll have x equal to plus or minus the square root of 16. So we have two possible values of x, which will be the additive inverses 4 and negative 4. And now with this system, again, I have the equations expressed not in x and y, but x squared and y squared. And in terms of solving for y, I can keep 16 for x squared and plug into either of these two equations. Now I'll just plug in for the first equation. So plug in 16 for x squared. So I have 16 plus y squared is equal to 25. And we have y squared is equal to 9. And we have with the square root property of equality, we have that y is equal to plus or minus, okay, the square root of 9. and we had the y is equal to plus or minus 3. So we have for number 15, we have for the solution, okay, so I have two distinct values for both x and y, from which we can spring forth 4 distinct points. So you can say we have 4, 3, negative 4, 3, also 4, negative 3, and also where both x and y are negative at minus 4 and minus 3 respectively.